Here we go, friends. Okay, few quick announcements as the term is coming to a close rapidly. Okay, so number one, I finally got in and you did the extra credit quiz assignment for Unit 1. Those have been put in the computer last night. If you've done your multiple choice retake, those are in the computer as well, unless you did it past 10 o'clock last night. FRQs I haven't gone all the way through yet for retakes, so if you've done those, it may or may not be in. Keep in mind you have till Tuesday at 9 p.m. Taylor, 9 p.m. on Tuesday is when the retakes are shutting down. So if you email me at 8:30 p.m. for the code on Tuesday, and even if I get it to you, know it's going to shut down, like close at 9. So I just recommend doing it before Tuesday would be the best case scenario. Okay. Keep in mind to get the access code, you either need to turn in your corrections to me and I'll give it to you in person in terms of like the code, or email them to me and I'll email you the code. Any questions though with end of term stuff as we're wrapping up here? Smiley faces will turn in on Tuesday if you're wanting to use those. Keep in mind if you don't need to use them because you're satisfied with your grade, then you get to carry them over to next term. So good. I guess this isn't going on the term, but it is due next time is your lab. I forgot to write that down. Take me as an assignment. So make sure you upload your lab and lab report by Tuesday as well. That will be like the first thing going on next term. So, okay, so where we're kind of looking at today to wrap up is we're first going to talk again about ionic bonding. What we're looking for again is the connection between this and this. So what we see happen at our level, like in the lab or in life, and how that can be explained by what's happening at the molecular level. So anytime you're talking about ionics at the molecular level, you need to have this picture in your head. Because that's pretty much-ish what it looks like, right? These big crystal lattices. I think we started talking about this last time, about why this one's so much higher, if I remember right.
Yes.
I think someone gave one reason already. Does anyone remember? Did we?
Yeah.
Yes?
Yeah.
Okay. Taylor, can you remind us what that reason was?
So the Mg and F2, the Mg is a 2 positive.
Good.
So it's stronger.
Yeah, and then sodium's +1. So one of the things is that the greater the charge equals a stronger force, which means higher energy. Now, when we do these explanations in class, mostly for time's sake, I write them very simple often with these this equals this equations. This format, though, is in a sense of how you should answer free response questions. Right? Your free response question, just translate this into more of a sentence, should have this connection. Magnesium, like Taylor said, has a +2 charge versus sodium, which only has a +1 charge. That higher charge causes a stronger force between the ions, which results in a higher lattice energy. Right? Don't just simply say, magnesium has a greater charge, so there's more energy. Right? Don't miss the middle piece of the understanding. Okay? All right. For a smiley face, I want you to tell me, would the lattice energy of sodium chloride be less than or greater than that of sodium fluoride? You can talk to your table buddy about it if you want.
Will be a threesome.
Yeah, you just write it.
Fluoride would have a higher lattice energy than sodium chloride. And so the closer. So I'm reading out my So,
but similar.
sodium chloride would be less. Right?
Yeah. Be a little bit less. I think it'll be less. Oh yeah, you took the reference
Okay. Someone, Evan, what's your vote?
We said sodium chloride would be less.
because it has another shell, so it's a lot bigger, and there's less of a force, or it has less molecular energy holding it together, so they're not as close together.
Good, because of distance, right?
Yeah.
Perfect, how you said it. How is my face if you said it is going to be less than sodium chloride? Because in this case, it's an issue of distance, right? And the farther away forces are from each other, right, the less force they feel. Keep in mind, anything that deals with positive and negatives goes back to Coulombic forces, which always goes to magnitude and distance, right? So in this case, our connection would be bigger size means greater distance, which means less energy. Okay? So what we're going to look at now is some of those properties we saw in the lab and justify at the molecular level why that would be. You'll notice when I flip the screen here, I'll give you a second to finish writing, that all the boxes are blank and I'm not going to write anything down in that. As we discuss it, I want you to write it down yourself, because sometimes there's a lot of power in you forming the words on your own rather than just taking someone else's words. Okay, but if you need us to say more about it, don't just leave one of them blank. Okay? Okay, so let's first talk about, okay, melting points. So we know, generally speaking, that all ionic solids have very high melting points. At the molecular level, anyone have a hypothesis of why that would be? Why is it so hard to melt ionic substances? Yeah, and what do you think?
Because they're held together so much stronger.
Yeah, and what are you having to, in a sense, break to melt it?
The lattice energy.
Like the lattice energy, right? Like you're breaking, in a sense, the bond that's holding them together. So that's why it's so high. Have a smiley face for that, Evan. That's a great hypothesis. Give me a second to fill that in. Now this next one, if you have a hypothesis you can share, it's a little bit more of a stretch because we haven't talked tons about water. But does anyone have an idea of why ionic substances would generally be soluble, like they dissolve in water? Yeah.
Is it because water is polar, so it also has like partial charges?
Yes. So what happens here is we have our little salt crystal, right? So on and so forth. Okay. In order for salt to dissolve, you once again are actually breaking kind of the lattice energy. The difference though is when it's in water, we often draw like Mickey Mouse because that's kind of how it looks. We'll learn how to draw these things actually today and next time. Where the head is the oxygen, the ears are the hydrogens. Okay? Water is an extremely polar molecule. What does it mean for something to be polar?
It shares like unequally, so like more electrons are on one side than the other.
Good, so we get this shift of the electrons in this direction, resulting in a negative side and a positive side. So in a sense, water is like a little magnet. So what it does is the water can come and attach, obviously in opposite ways. So the head attaches, because that's the negative side, so it attaches to the positive side. The ears attach to the negative side, and it gets pulled apart. So if we can magic school bus into a cup of salt water, what you would see is you would see your positive sodium surrounded by your little water molecules. So because water is polar, it's like a little magnet, it can break up this other magnet, right? Because positive and negatives are just attracted to each other. And we'll have a whole unit about solubility. So that's something we'll get more comfortable with as we go. But any questions on that? Okay, let's talk about conductivity. First off, in order to understand the molecular review, we need to make sure we understand what electricity is. Does anyone know what electricity actually is?
Isn't it the flow of electrons?
Yep, it's just electrons, right? So if I had carpet and went like this, and then shocked Kai, and you could see that little spark, right? Electricity is literally electrons, like lightning bolts are electrons. And the other word that I use as key is it's the movement. In order to conduct, you have to have movement of electrons. If they can't move, it can't conduct. So why, in that sense, why would ionics, when in solid form, why would they not conduct electricity? I just stick my probe into salt, it does not conduct. Taylor?
Because they're just like static, like they're not moving.
Yeah, it's a very rigid structure, right? You have positive, you have negatives, but there's no movement of the electrons. There's no movement of the ions either. Because the electrons have already moved in ionics, right? They've transferred over and then it just gets stuck. So, perfect. Have a smile face for that, Taylor. Building off of that, turn to your table buddy and tell them why then are they good at conducting once they dissolve. Ready, go. Tell them what you think.
They're tearing apart. It's like they weren't here to come.
Yeah, like in that picture or whatever, how they're all torn apart from like them positive water.
So then
They
it's
also
like,
moved like sort of like up.
goes through whatever electrons go through. Typically like actually like move around.
Okay, I heard it in a few different ways, and I think we're all there. But if you talk to your table partner about something about how once it dissolves, we now have movement of the ions, you can ask mine. This is why, once again, why distilled water, pure H2O, does not conduct electricity. But the ocean is extremely conductive because you have lots of salts and other things in there that allow it to conduct. But because pure water is not fully positive and negative, it's just a partial positive and negative, it doesn't conduct. So, questions on those? Sorry to make it a little bit more rushed than. Okay, let's talk about metals. I'm going to skip this for now, and we'll come back to it at the end, just because I want to make sure we get through the content. We can come back to that practice problem. Okay, so in terms of a metal, this is what your brain should conjure up when thinking about what metals look like. Okay, so if we had magic school bus into a metal, we'd see something like this. We have the positive metal atoms, so these are the actual atoms themselves, and they have released all their valence electrons, and they share them with everybody. The whole idea of that's the electron sea. Okay, they're shared equally, and they just flow. The reason why they do this is because metals don't have enough to transfer to make everyone happy, and they don't even have enough to share. So they just have to share and share and share some more. So let's talk about their properties of what. Oh, first off, there are two types of alloys with metals. Now, a metal alloy is when you combine two metals together. So like brass is an alloy. There's what's known as a substitutional alloy. Substitutional alloys are where you substitute an element that is very similar in size. And so the way it structures, it maintains the same setup. So for example, like brass is made of copper and zinc, would be a substitutional alloy because they're very similar in size. An interstitial alloy is when you get one that is significantly smaller than the other. So what happens is it actually fills in these spaces in between. Can anyone think of a reason why or a benefit to doing, question, Taylor?
Yeah, I was wondering would it be random like that? Like they're all just like in a random kind of assortment? Would that be how it actually would be?
That's a good question. I'm not sure, to be honest. My prediction would be yes, but there might be ways where they could get it to be less random.
Okay.
But if you simply just melted them together without doing other things,
Then it would look like
then
that.
I'm guessing I'm not going to do that still. But I wonder like if there's ways like with certain temperatures or maybe pressure or something where you could force it to line up. Good observation. I didn't notice that with this picture. Anyone know why we would do this type of alloy? What benefit it would have to a metal? Yeah, Matt.
Would it make it stronger maybe?
Yes, exactly. Yeah. Interstitial alloys increase the strength because it prevents them from bending as much. So great. Have a smiley face for that. Okay, let's talk about properties. Generally, metals have high melting points. Some of them are actually quite low. I don't know if I mentioned this before, but gallium is a metal, and it will melt in your hand, right? Very, very low. But why in general would we say that metals take a lot of heat to melt? Yeah, Harley.
I don't really know, but because the electrons are shared like with all of the atoms, I'm like it's all like one big bond.
Yeah.
And so like the bond is stronger.
Exactly, and to melt it, you're trying to pull them actually farther away from each other, right? And that electron C is holding them all together. So no, perfect. Yeah, just kind of think of we're trying to pull the little forces apart, the positive and negatives, and they're very resistant to it. Okay, why would metals never dissolve in water? I don't know why Alex did. Yeah, Zach?
Is it because like water molecules aren't strong enough to pull them apart? So, like,
Somewhat, yeah. And the other thing too is like keep in mind the positives, right? That maybe it would try to latch onto are already surrounded by this negative C, right? And so it just can't rip it apart like it does. Because ionics, it's very distinguishable. This is just positive, this is just negative. But a metal as a whole, it's like just all spread out, right? So you can, the electron C like protects it from being pulled apart. Going back to this electron C, why are metals good conductors as solids? That's that.
because the electrons are like flowing, so it's easier for electrons to go through them.
They're already flowing, right? So if you send more electrons in, it's just like, I imagine it like a crowd surf of the electrons. They just like pass them along, right? It just goes so quick. So yep, perfect. Yeah, that free flowing electron C just allows current to go through very quickly, very easily. And then the last thing that we see is that they are normally malleable. Now some take more force than others to bend, but all metals can bend if enough force is applied. Why would that be? Why are metals so malleable? Why do they allow you to bend them? Taylor?
Because like they have like an electron seed, so it's like it doesn't really matter where the protons are as long as they have electrons.
Yeah, if you think of them like, oh, it's a very flexible arrangement, right? It's not like ionics where it's positive, negative, right? It's like you can move those positives and the C will just flow with it, right? And so anytime you bend a metal, that's, I mean, in a sense what you're doing is you're just making that electron C shift around. Those atoms shift around, but they're still stable in their configuration. So, no, great observation. Any other questions on molecular view of ionics and metallic? Now, this table for covalence, we're actually not going to answer in this unit. And I'm sorry that it just kind of ends up being that way. Because before we can understand covalence, we have to understand them at the molecular level, and their picture is a little bit more complicated than just like how ionics and metallics are. So the rest of this unit, what we're doing is learning all about the structure of covalent substances. Today we're going to learn how to draw them in 2D, and then next time we'll learn how to translate them into 3D structures. Okay? All right, let's take a second. Everybody stand up. Need a quick stretch because I know we're doing lots fast here. While you're stretching, turn to your table buddy and tell them, what's the random question of the day? If you only had one piece of furniture in your room, what would you want? Say, who picked TV over bed?
Yeah.
The TV even considered. In that case, couch.
A really big like beanbag that goes like a big
Sleep on that. Outside and fall on the like imagine stepping into Wait, so much
Okay, here we go. Alright, so Lewis structures is the name for these 2D shapes for covalent substances. Now keep in mind, these are only for covalence. You don't ever really draw pictures of ionics because they're just positive, negative, positive, negative. Like I've never seen a test question that says, draw me a picture of salt. Okay, but learning how to draw covalence is very important because understanding how they are built helps us understand their properties. Covalence is also the family which I think most of you realized in the lab is the hardest to identify because they go both ways. Some covalents melt quickly, some don't. Some dissolve, some do. Some conduct, some don't. Understanding a structure of something explains everything about why it behaves. Structure is key to understanding chemistry. So, here's kind of some basics, and then pretty much we'll just practice drawing these shapes, okay? Few ways when these things share that can be drawn, okay? So when chlorine bonds with itself, we talked about before, they can share with each other, so sometimes they draw it by placing the 2 electrons in the middle. The more common, and I don't know, the way I like to do it is to translate those into a line, which is known as the bond. So lines on a Lewis structure are classified as a bond. This in a case right here would be known as a double bond. Because it's sharing twice. Okay, now each bond represents 2 electrons, which means a double bond contains 4 shared electrons. This right here would be known as a triple bond. Okay, so that means it's sharing actually 6 electrons, so each one counts as 2. Now keep in mind when they share, they now belong to both. And so the whole idea of why these bond is to satisfy that octet. If their octet doesn't or isn't satisfied, then normally they're not going to bond in the first place. Now, we know our not favorite thing in chemistry is all the exceptions. There are exceptions to that, but generally speaking, that's what happens. Okay, what we find is that the length of the bond will decrease the more bonds you have. So a triple bond is going to be shorter than a double bond, and a double bond is going to be shorter than a single bond. Now quadruple bonds, even though like for carbon, you could draw and it matches an octet, don't exist.
Isn't it just C4?
So it bonds in other ways with itself. You're correct, Taylor. It bonds actually in lots of different ways, but it will never quadruple bond with itself.
The quadruple bond not exist.
Not right now. Science, you never know, right? Maybe one day. Any thoughts of why it could never exist or doesn't exist?
Well, wait, actually, well, never mind, I didn't think that through.
You're good.
I was gonna say because there's like the little staircase separating thing. But if it
Oh.
but I was thinking like if it went with a different element, but with itself, or no.
Gotcha. Not a bad thought though. Anyone else have an idea of why quadruple bonds don't exist? What happens to the bond length the more bonds you have?
It gets really close.
What happens if atoms get too close together?
They like.
They push back, right? So one problem is the nuclei start getting too close. The second problem is how these things actually overlap. Okay, I drew it last time, once again, as a starting point. Like this idea, right? So we have like our nucleus, and then they overlap. That's not how it looks. I'll show you next time with balloons how it actually looks. And you'll find that a triple bond takes up most of the space. And there's really not much room for anything past that. So, okay, here are the things we need to be aware of in drawing Lewis structures. Number one, it's only valence electrons, right? Inner electrons don't bond. It's only the valence ones. If your molecule has a charge, that means there's an additional or less of your total electron count. Keep in mind that a negative charge means you have added extra electrons. A positive charge means you have lost those electrons. Okay? When we place our substances in our structure, generally speaking at this level, we're only going to have one thing in the middle and then other things will be around it. We'll draw a few that get a little bit more complicated than that, but generally speaking, that's how we'll go. The least electronegative atom is the one that will go in the center unless it's hydrogen. Why can hydrogen never be the middle of a molecule, Kimberly?
One electron.
Yeah, it only has one to share anyways, which means it only wants to share one time. And so hydrogen will only ever form a single bond. It can't form more than that, nor does it need to, right? It's satisfied with just 2 electrons. Okay? If you don't have enough electrons, that's when you then will have double or triple bonding. But that's not like the first thing you should go to. Don't double and triple bond to begin with. Then we'll learn about this thing known as a formal charge that helps you check like the accuracy of your picture. Okay? Everyone have that down if I go next? Okay, let's try one out. So we're going to draw a picture of PCl3. So my first step is to kind of build the skeleton. So if there's only one element, that's going to go in the middle. So I'm going to put phosphorus in the middle, and then I have 1, 2, 3 chlorines around it. My next step is to figure out how many valence electrons each of these are coming to the table with. So how many does phosphorus have? 5. So I'm going to just 1, 2, 3, 4, 5. How many does chlorine have? 7. Very good. So 1. And I'll be honest, sometimes the first picture that I draw for my Lewis structure may look a little rough, and then I'll just redraw like a cleaner picture for my answer. I take it as it's like my rough draft, right? 1, 2, 3, 4, 5, 6, 7. Okay, so step 1, draw your skeleton. Step 2, place your valence. Now, the whole idea is, well, they're going to bond, so start with a single bond. So a single bond is formed by 2 electrons being shared, so connect 2 dots and turn it to a line. Like so. After placing your single bonds, check your atoms to see if they're happy. Now I use the word happy, in meaning it has a full shell. So I'm going to draw some circles just as I'm talking to make it easier for them to see. But these circles are not part of the actual picture. So chlorine here has 2, 4, 6, 8 around it. So he's happy. This chlorine also has 8. He's happy. This chlorine has 8. He's happy. Check your middle. 2, 4, 6, 8. He's happy. Everybody's happy, which means you're probably right. And that's your Lewis structure. draw this like simpler, that one's not bad, but. So here's kind of a cleaner picture. Okay, terminology wise, these electrons right here are known as the lone pairs. Or the non-bonding electrons. So we would say that phosphorus here has 3 bonding pairs and 1 non-bonding or lone pair. Questions so far? Okay, let's try the next one. Let's draw HCN, cyanic acid. Okay, step 1, draw your skeleton. So we have H, we have C, we have N. Who's going to go in the middle of this structure?
C.
Why?
It has to be spin.
Yeah.
Good, so it can't be hydrogen, and then outside of that, it has the lowest electronegativity. Oops. So we have H, we have C, and we have N. Next step, put on your dots. Hydrogen comes to the party with 1. Carbon comes with 4. Nitrogen comes with 5. Okay. Then start with a single bond. So 1 bond will form here, 1 bond will form there. Hydrogen is satisfied because hydrogen only wants to, so I don't need to do anything there. But if I look at the other side, nitrogen only has 1, 2, 3, 4, 5, 6. So nitrogen needs 2 more electrons, so it's going to bond 2 more times. Okay, check your middle one. So nitrogen now has its 8. Carbon, 2, 4, 6, 8. Also has its 8. I'm drawing a cleaner picture here. So we have H, C, triple bonded to an N. And that's your answer. Questions on that one? Okay, let's have you try. Now, let's do this one together with the chart, and then I'll give you 2 ones for some side effects. Okay, let's do the bromate ion. BrO3 negative 1. So, we're going to put bromine in the middle with 1, 2, 3 oxygens around it. Oxygen comes to the party with 6. Fill your dots. Now, right away, you might notice that something already feels weird. Does anyone feel weird about this already? That's weird, Isaac.
Bromine can only make 1 connection.
So, using the simple rule, bromine only wants 1 more, right? Because it already has 7. There are atoms that can expand past 8. It's known. I know, love it. It's known as an extended octet. Atoms that can D block actually gives them room to go past the H that you learn often like in junior high, where they say, okay, 8 is how many things bond. Now the nice thing is exceptions, it's not so much really in this case where Lewis structures have to memorize them, because it's pretty much it's just going to do it. I know it's going to expand because there's 3 things it's bonding with. And so you just, pretty much after that what is you focus on the outside atoms. Get them their octet and then it's done. Only the central atom will expand. The outside ones can never have more than 8. Okay, so I also have something else interesting on this one because it's BrO3 with a -1 charge.
So 3 of them
So-
are negative 1 charge.
Ooh, great question, Kimberly. Nope, it's just a -1 charge to the whole. So in a sense, I have 1 bonus electron to add somewhere. So let's start with our single bonds first because we know that has to happen, otherwise it wouldn't be a theme. Okay? But we know for oxygen, how many times does oxygen need to bond?
Twice.
Twice. Okay, now I'm going to give my bonus electron to 1 of the oxygens, so that it is actually have its 8. The other 2 though don't have their 8, so the only other option is, should drew my dots a little bit differently here, but I'll clean up my picture, is to bond again. So my picture in a sense looks like that. So yes, technically bromine has 2, 4, 6, 8, 10, 12 electrons around it. Questions on that one? Now the final thing you need to do is when something has a charge, you have to show the charge on your molecule. So you put it in brackets and put the charge outside. Okay, you're gonna try some on your own or with your table buddy? Okay, try, just find, if you turn like 2 pages over, there's a blank page in your note packet.
Oh.
So you can do these on if you want. Okay, so for practice problem, let's do carbonate, so CO3 2 minus. Let's do HCF3. You can talk to your table buddy if you want, or compare with them after you come up with an answer.
Okay, so there's 2 extra.
I'm still drawing dots, bro. Hold on. Leave that.
And when you're trying to like balance things out, I always just focus on the outside atoms. And just whatever happens to the middle one happens to it. Yeah, that should help done, just set your pencil on your paper so I know you're finished.
Yeah, so one of
Wait,
these-
no.
Yeah,
One,
'cause-
two, three, four, five, six. Cause option one, two, three, four, five, six. And then give it one extra electron. There's a single bond here, which gives it two. Which means it'll be at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And you only have to add one electron.
Something's not working.
That's like six. Oh, no, you're finished.
Yeah.
I was like, one, two.
Stuck on the last one?
And then the first one.
That's good. Good job, man. Isaac?
Yeah, oxygen.
Does not make sense. Wait. This makes me mad. It's right above oxygen.
It has 6 as well.
It doesn't make sense. Would there be a little triple bond?
Yeah.
But then oxygen doesn't.
No, look, you can take it when they all have seven.
So you probably would just double bond this.
Yeah, this one would just have extra.
But can it do that?
Yeah. Cause that's what we talked about earlier.
But that was with the D block. Like,
Oh yeah, that's what we have to do to get it.
But
we're in a bit of a sticky situation.
I'm just gonna do this and hope for the best, cause out the other way it doesn't make sense. Cause then there, oxygen doesn't have, oxygen doesn't have that. And you have to balance out the outsides first, is what she said.
Why can't we just add a little next to right there and make everything not equal?
Yeah. Because then that would make it more equal. So that would make oxygen.
Wait,
Double bond.
Maybe that has something to do with resonance.
maybe there can just be one big line. A triple.
Triple one.
Oh, yeah.
I mean, that's the only way that makes sense. There's no other way.
Okay, I'm gonna start drawing, cause I think I've like everyone's done the first one. So I'll draw that just to confirm. I think they were going right, oh, they want to round. So for this one, you should have some carbon.
Oh no, this is
Oh wait, did I do that?
Give me a thumbs up or thumbs down, how we do on the first one? Get it? Questions on it? Okay, add a smiley face if you have that picture. Okay. Second one should look something like this.
Dude, if I get all 3 of these, I complete another percent. Dude, I need it.
There's number 2.
Shoot, I lost my place.
Put on that one.
Oh,
Okay.
wait.
Then our last one ends up being.
No.
Oh. Oh. Like that.
Is it a double bond?
Yeah.
There we go.
Double bonds on each side, lone pair on the middle. Wait, questions on Lewis structures before we talk about some board sessions.
Why can that one have
What
a
happened
10?
to
has 10 electrons.
Yes.
Why? Like mine
So,
has like 5 more.
Here's kind of the rule of why some can have more than 8 and others can't.
Why don't I just write
It's
this
all
in
once
my
again
phone?
because that D block.
Could've moved on that.
And because they're on the third period, which means we've started actually the third ring, right? The third ring has the ability to start filling up the D. So what we can get, this is kind of a rough picture, but if you actually draw orbital diagrams, so like sulfur's electron configuration looks like this, right? 1, 2, 3, 4. Okay? What happens is when things bond, sometimes their electrons move to other orbitals. And what sulfur does, actually, because it's bonding, what, 4 times here? So right now, sulfur only has room to bond twice. So what happens is it actually moves, here's your D, one of these electrons to the D orbital, and then it bonds 4 times.
Dude, what is sulfur's just like
Does that kind of make sense?
Yeah, sulfur doesn't care what sign.
So, here's kind of the one rule of like which ones can't. Like if you were ever like given one and like had to say like does this exist or not exist, elements on the second or first row can't expand their octet. Oxygen would never bond more than, or would never have more than 8 around it. But everything from third and below can actually have lots. So, I know, sorry. We don't really do those in general chemistry. We just ignore the exceptions, so.
Yep.
Any other questions so far? Okay, let's talk about formal charge. Okay, so formal charge is a mathematical equation where you can then test or check like the accuracy of a picture or of a Lewis structure, I should say. Now this is one, if you want to kind of put a big star by it, this is one formula that is not on your formula sheet. There's like maybe 5 in the whole year. All the rest we don't have to memorize, but this one is not there, so you need to like know how to do it without. Okay? So I'm going to write the equation in 2 ways. I'm going to write it the way the book writes it, and then I'm going to show you how I translate it. So the book says, or the official equation is you take the number of valence electrons. Now keep in mind this is atom by atom. Each atom in a molecule has its own formal charge. Okay? You take the number of valence electrons, you subtract 1/2 times, how they put it, electrons in the bonds. Minus the lone electrons. So total valence electrons of the atom minus 1/2 the electrons in the bonds minus lone pairs, or lone electrons. The way I interpret this equation is you do this. You take valence electrons, there's my abbreviation for valence electron by the way, minus lines minus dots. Okay, so for example here, if we look at these 2 pictures of carbon dioxide, technically both pictures satisfy octets, right? 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. So you're just going octets, both of them seem plausible. Formal charge is one way in which you can check and say, no, it's actually not going to do this. There's kind of 2 options. If a problem just says to pick a correct structure, but it doesn't actually tell you that finding the formal charge is part of the problem, you can often pick a right structure by just going back down to how many times something can bond. Oxygen has how many valence electrons to begin with?
6.
So how many times should it bond?
2.
Twice. Just by knowing that, I know this can't be a thing. So this is an incorrect structure. So if you just had to pick, lots of times you don't have to actually find formal charge. But I have seen problems where they want you to actually calculate their formal charges, so here's how we do it. Okay, so we take it for each individual piece. So oxygen has 6 valence electrons. It has 2 lines, -2, and 4 dots. So this oxygen has a formal charge of 0.
Oh. And if it equals 0, is that like correct?
Yes, most likely. It won't always be 0, but we want to be as close to 0 as we can.
Okay.
Okay, in this case, carbon has 4, -4 lines, -0 dots, so it is also at 0. Now, technically, you don't have to, I'm just showing you all the works, you know where it's coming from, but obviously this could be something you just figure out in your head, right? Oxygen is 6 minus the 2 lines minus the 4 dots, so it's at 0. Which, kind of like the observation Taylor said, is things that are at 0 are most likely the stablest configuration. But just to compare to this side, so now this oxygen is 6 minus 1 minus 6, so it's at a -1. The carbon's at 0 still, but this oxygen would be at 6 minus 3 minus 2, so it's at a +1. Which is why that is not the correct Lewis structure. Yeah.
Why is that carbon at 0?
Because it's still, so it has 4 to come with, right?
Oh, okay.
And it still has 4 lines, even though they're in different spots. So, good question though. Questions on formal charge? Yeah, Bryce.
So like on this one, technically if you add up all of the things, you get like 16 minus 8 minus 8. Are you like, does that work for all of them, or is that just like something that just works for this one?
Like if you combine,
Yeah, like if you combine all of the
like
valence
total electrons,
Yeah.
I think you'd get 0 for both. So yeah, you have to do it individually. So, good answer, great question though. Other questions on that? Okay, let's try a practice problem for another SNI base today. See if you can determine of these 3 structures, which would be the correct one. Ready, set, go.
I'm gonna do some guess.
That wouldn't be 0.
So your final answer should tell me
Oh,
A, B, or C.
Yeah, because that one, because you want it, like if it wasn't
Yeah.
because if there wasn't an extra electron, that would be a 0. Which means that it's A.
Base.
You have to double check for the messed up. Like when I was talking about carbon, because I messed up the valence electron.
Okay, sorry to rush you, but I'm gonna start going through it just so we have one last thing I want to talk talk about, so we're already on this.
Josh.
I heard a few things, or I heard Kimberly say, and I think someone else over here said, like, technically since this is multiple choice, you could see if you could answer without doing formal charges. In this case, I narrow it out and say it's not C pretty quick. What about C helps you know, like, that just doesn't work?
There are 8 there's 6 valence.
Yeah, so sulfur is never gonna form a triple bond on the outside, right? Now it can expand past a normal 2 on the inside, but on the outside, they never go past how many they have to share. Now both of these two are, in a sense, plausible. They kind of balance in the sense of nitrogen likes triple bonds, but sulfur likes double bonds. So it's like, well, which one is better? So what happens is if you do your formal charges, this one ends up being a -1, this is a 0, and this is a 0. And this one is 0, this one is 0, and this is -1. That's how your formal charges should fall if you calculate them.
Should that be a -2?
No.
This one's a -2 on that one. Are you looking at the far one? Because it's 5 minus 2 minus 4. So then when you just have one negative or one charge,
Is it sulfur?
the rule that you go to is it goes to the negative charge should dwell on the more electronegative atom. So nitrogen is more electronegative than sulfur, so it is
Okay.
If you got it right, you can have 2 smiley faces. If you got it wrong, but you did the right formal charges, you can have 1 smiley.
Okay.
I know.
I am so confused.
Raise your hand if it's not that right.
How can you do formal charges?
So on formal charges.
Right, we both did it.
So you just find how many valence electrons it has, right? Minus how many lines are in the picture, minus how many dots are in the picture. The goal of the more zeros, the more stable it is.
Yeah.
Does that help clarify a little bit?
Kind of.
Okay. We can practice some more at the end if you want to. Okay, last thing we need to talk about here, everybody, is this thing known as resonance. Okay? So what happens is sometimes you can draw a structure, and your neighbor might draw a structure, and they look pretty much the same, but they almost might look like mirror images of each other, right? So for example, ozone is O3, so it's oxygen bonded to oxygen bonded to oxygen. Okay? And if you balance out the electrons, what you get is a picture like this. Or a picture like this. Now on paper, these pretty much look like it's the same thing, it's just a mirror image of it. But in real life, these are actual atoms. And so it's important to know, like, well, where is the double bond on this oxygen or is it on that oxygen? Well, scientists have found out something very interesting with structures like ozone and these mirror image idea. When they go in and measure the bond length, okay, because they can actually measure the length of bonds, right, scientifically in the lab, they found that the length of the ozone bond, I'll come back to this in a second, but let me go to the picture here. They found that a double bond is this length, a single bond is that length, so 148. A double bond is 121. But the length of ozone is 128. The length of ozone falls between the length of a single bond and a double bond. Any idea of what's happening then?
Half bombs.
Kinda.
Why?
What happens is because electrons
Why did it do that?
are mobile things, right? Electrons don't just stick somewhere, but they're constantly moving.
It goes around all of them.
Is it goes around everywhere. And because it's so moving so fast, to ours, it almost looks like it is everywhere. to me, it's kind of like the idea of a fan, right? If you turn a fan on while it's spinning, it looks like the fan is everywhere, right? It's continuous. If you stop the fan, well, then you can actually see the separate blades. That's kind of the same idea with these electrons, is in real life, it's everywhere. If you could pause it for one moment, it could look like this or it could look like that. So your answers for Lewis structure, so this is known as resonating. So if a molecule resonates, your answer needs to be both pictures. And then we draw this arrow in between. Now, I gotta find out once again, because I'm not sure. We're learning like inorganic chemistry. In organic chemistry, we actually often represent them by these dashed bonds instead. I don't know if that's like acceptable for the AP people. I'm okay with that for homework. So if you want to do dashed bonds instead of lots of structures, I'm okay with that.
How many structures does it get up to?
3 would be the most. So, but yeah. Questions on resonating? Okay, that's like quiz 2.6 in the back. Now remember, you guys also, sorry y'all, a few more AP master quizzes. You have also quiz 2.3 and 2.4.
And 2.6 lab is due on Tuesday.
And the lab is due Tuesday. But then it's fall break. And that's break, then everything is break. See ya. Okay, someone got through pretty much everything we needed to like get refined on the board. But someone remind me next time that we still need to like talk about using on this section.
6 points, 4 to 6 points.
Which is like, you guys can all say bye to that student.